What's poppin', dogs? Mr. Allen here with a problem involving concentric circles, which means that they are circles that share the same center. You could have 2, 3, 4, whatever amount of concentric circles, making a sort of bullseye-looking thing. For this one, they have radii of 8 inches and 17 inches. Fun fact, I wrote this for a reason. IN, abbreviation for inches. 2 apostrophes also means inches, okay? Just in case you didn't know, fun little fact. Now, a chord of the larger circle is tangent to the smaller circle. We want to find the length of that chord. And you might be wondering, why in the heck am I holding this right now? It's because I'm going to draw a couple concentric circles for you with my compass. Now, I got to make sure that all fits nicely on here. I think this will be a good spot right around here. Hopefully I don't run into my words up there. Woo! Oh, I just got the E on the. That's okay, though. We will survive. Boom. Nice. There's the center. Okay, and then I'll make it a little smaller now for our second of the 2 concentric circles. Pop that in the center. And then let's see if we can do this thing without... already messed it up. There's a lot of pressure here, guys. There's a lot of pressure. I'm very nervous. It's kind of hard to stay put on the board there. It's just... what I did is I cut off the eraser from a mechanical pencil and just like pulled it out. That's the tip of this compass here that helps it hold into place. All right, a little DIY compass action. But there we go. We have 2 concentric circles now. And we have a chord of the larger circle that lies tangent to the smaller circle. So let's draw that up. And now where you draw this is totally up to you. But I have some ways that I like to go about it. I either draw it up at the top here, horizontal, or at the bottom, horizontal. And I'm going to do it over here at the bottom and as horizontal as I possibly can. And I want to try and get it so it looks nice and tangent. Oh, that's beautiful. Okay. So that's the length that I'm looking for. This is what I want to figure out. Now I'm given that I have radii of 8 inches and 17 inches. So where do I draw those? I can draw them anywhere. There's an infinite number of radii in a circle, right? I can be like, shoo, 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 all over the place. Doesn't really matter. However, there's a common strategy in mathematics that I suggest you follow. If I can get a right triangle somewhere, I can math with that, okay? If I can somehow put a right triangle on this picture here, I can math with that. If I have a cone or a pyramid or anything else and I can somehow get a right triangle within that, 3-dimensional space, I can math with that. So let's see if we can get a right triangle going. Well, I could draw my radius of the smaller circle straight down to the point of tangency here. Whoop, boom. Now, what's significant about a radius drawn to the point of tangency? And what I'm saying here is that although this is a radius of the small circle, it's also, if I were to extend it out, if I continued it on, I'm just going to do a little dash line here. If I continued it onto the edge of the larger circle, it's also a radius of the large circle. Well, it perpendicularly bisects. Boom, okay? So if a radius is drawn to the point of tangency to a chord, it's perpendicular. Okay, that's for the small circle. So I drew my radius to the point of tangency of a chord. It's perpendicular to that chord. Now, when I extend that all the way through to the large circle, and now it's a radius of the large circle here, if a radius of a circle is perpendicular to a chord of that circle, then it also bisects that circle. So we've gone to like a couple different theorems that have just happened here within these circles, okay? Cool. So radius drawn to the point of tangency is perpendicular, and then a perpendicular radius to a chord of the big circle then bisects that chord. Bisecting the chord, perpendicular, perpendicular to the chord, bisecting. It is reversible, which is dope. Converse would be the fancy math word. Okay, now what? Now what? Well, perhaps I could label this as 8 inches. That'd be good. What about my radius of the large circle? Where could I draw that? Well, again, I could draw it anywhere I want, but you may see a right triangle forming here, dogs. And if you do, you are absolutely correct. Let's go ahead and draw that in. Boom. This is 17 inches. Nice. If I got a right triangle, I can Pythag that, right? I can hit with some Pythag. We can get 8 squared plus, I don't know what, we'll call this x, squared equals 17 squared. And if you're like, hey, Mr. Allen, isn't that a triple? You are right. It is an 8, 15, 17, triple, okay? So you can either solve it, 64, 289, subtract square root, blah, 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 and we get 15. Or if you remember your triples, we have 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. Those are the most common. There's also a 9. Whoa, that's a terrible 9. 9, 40, and 41. Far less used. The main ones are those top 4. But, you know, you can go on. There's a lot of them. I think there's an infinite number of them. Anywho, I think there's an infinite number. There's got to be. It's numbers. All right, so those are your 4 main ones, though, for your Pythagorean triples that'll help you solve some stuff. Is this my answer, though, folks? No, it is not my answer. What is my answer, though, is if I took this 15 right here, and I also applied it over here, because we know that the radius of the large circle, if it's perpendicular to this chord, it also bisects that chord, so they're both the same. 15 plus 15 is 30. Let's include units, inches. That is my length of the chord. Dang. That was dope, dogs. Hope you enjoyed it. Concentric circles. Looks like a bullseye. Look for right triangles within the diagrams. Anytime you can, see if you can throw a right triangle down. It doesn't always work, but if it does, that's money. All right, have a wonderful day, guys. Thanks for watching, and stay dope.